I want you to just picture something in your mind right now. Imagine a person standing in one of those sterile, ultra-clean manufacturing rooms.
Oh, yeah, the ones with the massive air filter.
Exactly. And they are wearing one of those full-body white bunny suits, completely covered from head to toe. But in their hands, they're holding what looks like, well, it looks exactly like a massive, gleaming copper floor tile.
Right, just a heavy, solid, shiny square.
Yeah.
Which is a really striking visual. And I mean, if you have any background in technology, it's an image that immediately breaks your brain a little bit.
Because it's not a floor tile at all. It is a single computer chip.
Yep.
And the reason a massive copper plate like this even exists is because the biggest players in artificial intelligence are, quietly trying to rewrite the laws of physics and basically the rules of the entire tech industry.
Yeah, they really are.
So today's deep dive is all about the Cerebras WSE3. That stands for Wafer Scale Engine 3rd Generation. We're looking at some incredible reporting by Aaron Rose from the tech-reader AI Digest, alongside some very revealing SEC S1 financial filings. We really want to unpack a piece of technology that completely defies intuition.
It really is a paradigm shift. I mean, we are entirely conditioned to think of processors as these microscopic squares of silicon, right? The things hidden deep inside our phones or laptops.
Right, you need a microscope to even see the circuits.
Exactly. So to see one the size of an actual dinner plate, it's just jarring.
Yeah.
But Cerebras didn't do this just as a PR stunt. They decided to throw out decades of established semiconductor manufacturing rules to solve a massive paralyzing bottleneck in modern AI.
Okay, let's unpack this traffic jam, because I think anyone listening who has ever, watched a ChatGPT prompt just sit there and spin during peak hours, you've felt the effects of this bottleneck firsthand. So why are traditional chips struggling to keep up?
Well, to understand the problem, let's look at how every other chip you've ever interacted with is made. Normally, engineers start with a large circular silicon wafer, specifically a 300-millimeter wafer, which looks a bit like a shiny metallic pizza.
Okay, a metallic pizza, I got it.
Right. And they etch all the microscopic circuits onto it. Then they take a saw and literally physically slice that circular wafer up into hundreds of tiny, identical little pieces.
Like slicing up the pizza.
Exactly. Each one of those tiny cutout pieces is packaged up and becomes a single chip. So the wafer is just the raw material, and the tiny slice is the actual product.
So Cerebras looked at that standard operating procedure and essentially asked, what if we just skip the slicing part?
Yeah, they just kept the whole pizza. The Cerebras WSE3 is the entire 300-millimeter wafer, just squared off at the edges.
That's wild.
It is, and they partnered with TSMC, which is basically the premier silicon foundry in the world. They're the same people who make chips for Apple and NVIDIA. And they use TSMC's 5-nanometer process.
Which is tiny, right?
Unbelievably small. We are talking about features roughly the width of a few strands of DNA. And across that single uncut piece of silicon, they managed to etch 4 trillion transistors.
Wait, 4 trillion?
4 trillion.
That is, the human brain has what, maybe 86 billion neurons? So we are talking about numbers that almost lose their meaning here. And the article also mentions it has 900,000 AI-optimized cores and 44 gigabytes of on-chip SRAM. Let's actually define SRAM for the listener, because that seems critical.
Sure. So SRAM stands for Static Random Access Memory. Think of it as the ultra-fast scratch pad memory that is physically glued right next to the processor's drain.
Right.
In a normal computer, your main memory, your RAM, is sitting somewhere else on the motherboard. When the processor needs data, it has to send a signal down a tiny wire, grab the data, and bring it back.
Which takes time.
Exactly. In the context of AI, doing that billions of times a second is an absolute eternity.
Okay, I want to try an analogy here to see if I'm really grasping the physical scale of this. Think of a traditional AI setup, using standard tiny NVIDIA chips, as a sprawling, decentralized city.
Okay, I like where this is going.
You have millions of workers, which represents your data, and they have to constantly commute back and forth across these slow, congested bridges.
And those bridges are the network cables, right? The physical wires and the switches connecting all those separate tiny chips together.
Exactly. So during a massive AI workload, these separate chips are trying to talk to each other, which means the workers are driving across those bridges billions of times a second. It wastes time, and honestly, all that driving wastes energy. So what Cerebras basically did was demolish the decentralized city and build one single colossal skyscraper.
That is a fantastic way to look at it, because
Yeah.
the chip is the size of the entire wafer. Everyone lives and works in the exact same building.
Right. You pack all that 44 gigabytes of SRAM scratch pad right next to the 900,000 compute cores. No one ever has to leave the building. The commute is just eliminated entirely.
And the performance results of eliminating that commute are staggering. I mean, because everything is happening on one unbroken piece of silicon. The internal communication speed, the fabric connecting all those cores, runs at 21 petabytes per second.
Wait, petabytes, not megabytes, not gigabytes.
Not even terabytes, petabytes.
That is insane.
And when it's housed in its dedicated server system, which is called the CS3, it actually delivers 27 petabytes per second of aggregate bandwidth.
Wow.
Let's frame that against the current industry gold standard so it makes sense. That is more interconnect bandwidth on one single chip than you would get from 1,800 of NVIDIA's flagship DGX B200 servers combined.
You're kidding?
No, it's real. If you look at NVIDIA's massive NVL72 rack, which is an entire refrigerator-sized server rack packed with 72 GPUs, a single Cerebras CS3 provides over 200 times the interconnect bandwidth of that whole rack.
Okay, that is just hard to wrap your head around. One dinner plate chip outperforming an entire room full of flagship servers in terms of how fast data moves. But this brings up a massive red flag for me.
What's that?
Well, if building a giant skyscraper chip solves the AI traffic jam so flawlessly, why didn't NVIDIA or Apple do this years ago? I mean, they have all the money in the world.
That is the big question. And the answer is because according to the traditional laws of semiconductor manufacturing, what Cerebras did should be mathematically impossible.
Mathematically impossible.
Yes. The engineering miracle here isn't just the size. It's the fact that they got it to work at all without throwing the entire thing in the trash.
Wait, explain that. Why would it go in the trash?
Well, let's go back to that standard manufacturing process we talked about,
Right.
where you slice the 300-millimeter wafer into hundreds of tiny chips. Silicon manufacturing is incredibly precise, but it is literally never 100% perfect.
Right, there's always dust or something.
Exactly. There is always a microscopic speck of dust or a slight chemical variance. There are always microscopic defects on the silicon. In a normal process, if a microscopic flaw lands on one of those tiny sliced-up chips, you just throw that one broken piece away.
And you still have like 399 perfectly good chips left.
Right? The yield is still great.
But wait, if your chip is the entire uncut wafer, and there are always microscopic flaws, you're saying every single wafer they make inherently has broken parts on it. Do they just leave the broken pieces inside?
What's fascinating here is exactly that. Yes, the physical flaws remain on the silicon, because a single defect would normally ruin an entire wafer, meaning your one and only massive product goes in the trash strip. Cerebras had to completely pivot their engineering philosophy.
How so?
They essentially abandoned the traditional pursuit of manufacturing perfection and instead designed for architectural resilience.
So they're expecting failure from the jump.
Exactly. First, they shrunk the individual processing cores down significantly. A single core on this wafer is just 0.05 square millimeters.
Which is how small exactly?
To visualize that, it's about 1% of the size of a single core on a top-tier NVIDIA H100 chip. And because the cores are so incredibly tiny, they can pack an excess of them onto the wafer.
Ah, I see.
They didn't just put 900,000 cores on it. They included extra redundant cores scattered throughout the whole layout. This creates what they call a fail-in-place architecture.
Okay, fail in place. Returning to our skyscraper analogy from earlier, if a worker tries to use a broken elevator shaft, the whole building doesn't collapse. You just put up a detour sign and send them to the elevator next door.
And that detour happens physically, right at the hardware level. When Cerebras tests the wafer in the factory, they identify exactly where those microscopic defects are. The system then permanently shuts down those flawed sections.
So it just blocks off the bad roads.
Yep. The on-chip fabric, that microscopic highway connecting everything, literally updates its routing tables. So when a data packet is traveling across the chip at the speed of light and approaches a broken core, the hardware automatically diverts it to one of the redundant functioning cores nearby.
That is brilliant. It's essentially self-healing infrastructure. The data just takes the bypass lane.
And this wonderfully complex detour system yields 100 times better defect tolerance than conventional processors. They mathematically proved you don't need the wafer to be perfect. You just need it to be incredibly resilient.
Okay, but we have to talk about the physical reality of powering this thing. We have this resilient 4 trillion transistor skyscraper, But you just can't cheat physics.
Yeah, you really can.
If you cram all that computing power into a 21.5 centimeter by 21.5 centimeter square, you are concentrating an astronomical amount of electricity into a very, very tiny space.
Right.
The heat must be absolutely terrifying.
It is an absolute beast. You do not just plug this WSE3 chip into a standard computer motherboard. It requires its own massive dedicated housing, which is the CS3 system.
Yeah.
And this system takes up 15 U of rack space in a data center.
Let's define that for anyone who hasn't walked through a server farm. So a data center rack looks like a tall metal bookshelf, and a U is a standard unit of measurement for those shelves, right? About 1.75 inches.
Right.
So 15 U is what? Roughly the size of a mini fridge? Or maybe a large dishwasher.
That's a really good estimate. And inside that mini fridge, standard air cooling, like the little fans blowing inside your laptop, is completely insufficient for the density of the compute happening on that single plate of silicon.
So how do they cool it?
The chip is internally liquid-cooled.
Liquid-cooled, meaning they are actively pumping liquid through a multi-million-dollar supercomputer to keep it from melting down into a puddle of slag.
Yep. The heat is removed and transferred out of the system. It's either dispersed by massive industrial fans or plumbed directly into the data center's facility water lines. And they rely on completely redundant water pumps to ensure the flow never, ever stops. Because the power draw is immense.
Yeah, let's translate that power draw for the listener, because the numbers in the Tech Reader article really stood out to me. A single CS3 system draws 23 kilowatts of power.
Which is a huge number.
Right, and 23 kilowatts might just sound like technical jargon to some, but for reference, that is roughly the peak power draw of a large American home.
It's massive.
Yeah.
And remember, a standard data center rack can fit 2 of these CS3 systems.
Which creates a staggering footprint. It means one single rack slot in a server farm is drawing the equivalent electricity of 2 entire large suburban houses.
Exactly.
Imagine 2 houses running their central air conditioning, their electric dryers, and all their lights at maximum capacity simultaneously. And this server rack is doing that 247 with water constantly flowing through it to manage the extreme heat.
If we look at the implications of that, it just highlights the extreme physical reality of modern AI. You can't just run this thing in an office closet. You need specialized data centers. You need reinforced floors to hold the weight of all those water systems, and massive city-level power agreements just to turn these machines on.
Which means you need incredibly deep pockets.
Yeah.
The sheer physical requirements of this hardware perfectly explain the incredible business maneuvering detailed in those SEC S1 filings.
Right. The financial side of this is just as crazy.
Cerebras recently went public at a $95 billion valuation. But if you dig into the paperwork, the real story isn't just about their stock price. Here's where it gets really interesting. It is about their deep, almost entangled relationship with OpenAI.
The creator of ChatGPT.
Yep.
OpenAI looked at this massive water-cooled copper plate and recognized that it could be the exact solution to the inference traffic jam you mentioned earlier. But they didn't just place an order for a few servers.
Oh, no, they went way further.
They fundamentally intertwined their corporate future with Cerebras. They signed a $20 billion master relationship agreement for 750 megawatts of inference compute capacity.
$20 billion. That is just an earth-shattering amount of money for a hardware partnership. But the S1 filing reveals they went even further than that. OpenAI essentially acted as a bank for them. Right?
They did.
Yeah.
Alongside that $20 billion agreement, OpenAI loaned Cerebras over $1 billion via a secured promissory note that matures in 2032.
That's a huge loan.
But if we connect this to the bigger picture, the most crucial detail is tied to the equity. Tied directly to that master relationship agreement, OpenAI received warrants to purchase 15% of Cerebras' fully diluted equity.
Okay, let's pause and define what a warrant is in this context. It essentially means OpenAI gets the contractual right to buy 15% of Cerebras' stock at a predetermined, likely highly favorable price, regardless of how high the stock actually goes in the future.
Exactly. The SEC filing explicitly describes this equity access as a material inducement to enter the deal. So OpenAI effectively said, look, we will give you $20 billion of guaranteed business to scale up your massive manufacturing, but we demand the right to own 15% of your entire company in return.
That is aggressive vertical integration. OpenAI isn't just buying chips from a vendor anymore. They are taking a massive financial and operational stake in the foundational hardware layer itself. And they managed to do it before their own potential IPO.
Think about the different ways this plays out. It is a brilliant hedge. If the global demand for AI inference continues to explode, like if billions of people start using AI for daily tasks, OpenAI has already locked down the physical hardware capacity to handle all those requests at high speed. They control the specialized pipes.
And on the flip side, if Cerebra succeeds in becoming the gold standard for AI hardware and their valuation skyrockets beyond that 95 billion mark, OpenAI's 15% equity warrants explode in value. They make billions just off the stock, so they win either way.
That $20 billion agreement is less of a standard procurement decision and much more of a strategic enclosure. They're capturing the ecosystem.
Strategic enclosure. I really love that term. They are building a physical moat out of copper and silicon. But, hearing all this, the blazing 27 petabytes per second speed, the massive $20 billion OpenAI partnership, the $95 billion valuation, you would be entirely forgiven for assuming that NVIDIA's reign as the king of AI hardware is officially over.
It certainly paints a picture of massive, sweeping disruption.
So, what does this all mean? Are we witnessing a David versus Goliath story where the dinner plate chip finally slays the giant? Because Aaron Rose highlights some benchmark tests in his article that are pretty wild.
Yeah, the benchmarks are impressive.
The Cerebra CS3 is up to 21 times faster than NVIDIA's flagship DGX B200 on large language model reasoning workloads. 21 times faster, and it boasts a 32% lower total cost of ownership.
Those benchmarks are accurate, but we desperately need an impartial reality check here.
Okay, let's hear it.
Cerebras has achieved something monumental in hardware engineering. But to understand the market, we have to distinguish between the two distinct phases of artificial intelligence, which are training and inference.
Wait, let me see if I have my head around this. If I try to put this into an analogy, is it fair to say that training an AI model is like going to law school and studying for the bar exam? It takes years. You are absorbing millions of pages of textbooks, figuring out the rules, and it requires agonizing brute force effort to build that internal knowledge base.
That is an excellent analogy. Training is the process of building the AI model from scratch. You feed it trillions of words and images, teaching it how to recognize patterns and build its internal logic. It requires months of raw computational power. Inference, on the other hand, is what happens after the model is trained.
So inference is the lawyer actually practicing law. A client walks into the office, asks a specific question, and the lawyer instantly references their knowledge to serve up an answer.
Precisely. When you type a prompt into ChatGPT and it generates an answer in real time, that is inference. It's the model reasoning and serving up an output based on what it already learned. And Cerebras is incredibly undeniably fast at inference.
Because of that huge bandwidth we talked about.
Right. For serving model outputs to users, where memory bandwidth and communication speed are the top priorities, their wafer-scale chip is an absolute monster. That is precisely why OpenAI, which has hundreds of millions of users demanding instant answers every second, wants them so badly.
But what about the law school part? What about the training?
Well, that is where NVIDIA still completely dominates. NVIDIA currently holds roughly 90% of the AI accelerator market share. To put these companies in financial perspective, NVIDIA generates approximately 423 times the revenue of Cerebras.
Oh, wow. Okay, so Goliath is still Goliath.
Absolutely. And perhaps most importantly, NVIDIA has an incredibly deep, decade-in-the-making software moat called CUDA.
Let's explain CUDA. That's essentially the programming language that developers use to write AI applications, right?
It is. It's the software platform that allows the code to talk to NVIDIA's hardware. Because NVIDIA has been the only real game in town for so long, almost every AI developer in the world is completely fluent in CUDA. It is very, very hard to convince an entire industry of developers to abandon a language they know perfectly to go learn how to program a totally different, massive piece of hardware.
So Cerebras isn't killing NVIDIA?
Not at all. It is not a zero-sum game. What Cerebras is doing is carving out a highly specific, incredibly lucrative niche. They found the exact workload inference where their massive interconnect bandwidth provides an insurmountable advantage, and they are moving to own that specific space entirely. NVIDIA continues to rule the training phase, while Cerebras tries to monopolize the daily application phase.
Got it. They aren't trying to beat NVIDIA at their own game. They basically invented a completely new game where the rules heavily favor a chip the size of a dinner plate.
Exactly.
Well, let's summarize the journey we've just been on, because the scale of this is amazing.
Right.
We started by looking at a microscopic problem, how a single tiny manufacturing defect usually sends a silicon wafer straight into the trash.
Right.
We saw how Cerebras threw out the rulebook, embracing those defects with the fail-in-place architecture, right? Those hardware-level detours that allowed them to build a 4 trillion transistor plate. Then we translated that into real-world infrastructure, realizing that cooling and powering just two of these systems takes the electricity of two large American homes.
Which is still just crazy to think about.
It is. And finally, we unpacked the $20 billion maneuver by OpenAI to buy their way into the foundational hardware layer. The reason you need to care about this is simple. The battle for the future of artificial intelligence isn't just happening in the software code anymore. It's happening in heavy physical hardware. And the biggest companies on Earth are ripping up the old rules of physics and business to make sure they win.
It is a remarkable convergence of extreme engineering and aggressive economics. And it really leaves us with an incredibly important question to consider, building on that idea of OpenAI's strategic enclosure from the SEC filings.
Yeah.
Think about the long-term implications here. If the company that designs the world's most dominant AI software models like OpenAI also ends up essentially owning and controlling the very physical, highly specialized pipes required to run those models fast and cheap, does the line between a software company and a hardware monopoly completely disappear? We might be looking at a near future where whoever controls that physical gleaming plate of silicon ultimately dictates what AI software is even allowed to become.
That is a heavy thought to chew on next time you imagine that engineer in a clean room holding what looks like a copper floor tile but is actually the physical blueprint for the future of the internet. Thanks for joining us on this deep dive.